To continue on here. That's the wrong pen. Let me try this one. We are 17, I think. So we've been talking about electrochemistry. That's to do with redox, I think. There you go, redox. So a reminder, redox reactions, right? There is your oxidation, which is the guy that kind of loses some electrons. There is the reduction, which is the one that gains electrons. And we also have our oxidizing agents, right? Remember, the oxidizing agent is the substance that gets reduced. The reducing agent is that guy that gets oxidized. And we can basically figure out, right, who's being oxidized, who's being reduced by, again, following the oxidation state are numbers from left to right on the arrows there. And again, as we talked about, if you want, you can use just a basic number line to help you figure out if something's going through oxidation or reduction based on their oxidation states. Again, when things lose electrons, they become more positive. So if you see the oxidation state move towards the positive direction on the number line there, it is going through oxidation. And if you see it's going more the negative direction there, it is going through reduction as it gains electrons and becomes more negative. We talked about balancing redox reactions in an acidic and basic solution with water, some H pluses. Then we got into really sort of the heart of the chapter there, which was some galvanic cells. And your basic galvanic cell, we have an anode side and we have a cathode side. Anode is where oxidation occurs, reduction there occurs on the cathode side. And typically speaking here, got some solutions, maybe some wonderfully drawn electrodes on each side, maybe connected there, maybe big voltage happening as well. And also connecting both of these guys here usually is our salt bridge. And a little artsy there, so don't fall out. So what happens here, obviously on the anode side, we have oxidation occurring, so that's going to release those electrons. The cathode side, a little bit more positive, going to drag the electrons across. And remember that these guys will lose electrons. So basically, they're going to go for a swim into the solution. As they lose those electrons, become ions. And when those electrons come this way, they're going to then take some of those ions out of solution and become a solid in this case. Remember, the function of salt bridge, as we talked about, is to keep everything functioning correctly. There is a potential difference between the cathode and the anode side, which allows those electrons to be pulled. Without the salt bridge present, again, you would get the buildup of the wrong sort of charge that you want. So, for example, again, on the anode side, if you did not have that salt bridge, you would get a buildup of positive charge, which is not great because the electrons will not want to go anywhere. They'll just kind of hang out there and you won't have those flow of electrons happening. In addition, on the cathode side, you would get a buildup of a negative charge, which also would repel the electrons to stay on the other side. So again, the salt bridge is really what kind of keeps the charges in check on both sides of your galvanic cell, and it allows it, thank you. It allows the electrons to continue to do work and go out onto the wire. We could calculate the E of the cell, and that is a couple equations we talked about. You could take the E of the cathode minus the E of the anode. Remember that we use the SRP values there, or that table, and that stands for their standard reduction potential. And remember that if we use this equation here where we subtract, you do not want to change the sign of what you find in the table. And that's because these are all reduction reactions in that table. And one of your reactions does need to be an oxidation reaction, which is technically the opposite one. And that is why the minus is here. It will change the sign for your anode without you having to think about doing it. If you do want to change the sign on your anode side, then you should add them together like we talked about. So again, if you change the sign, you should add. If you want to just take the value you find in the table and not have to worry about changing anybody's sign, then put it into the one where you subtract and you should get the same. Now, remember that in the absence of any information about how the reaction takes place, the more positive SRP value is typically the one that gets reduced, and that typically would then mean that is your cathode in that case. So the one with the more positive SRP value should be your cathode. If they do give you information about how the reaction is going to happen, or they give you an equation or tell you in words how things are reacting, you do need to look at the equation and figure out who's being oxidized and who's being reduced. And then that would help you determine which one's your anode and cathode. But again, in a couple examples like we did, I think last time, if they just kind of say, hey, you built the cell out of these things, you could go with the more positive one would be your cathode. Any questions on any of that stuff there? All right, so I think we laid up here probably. I feel like this looks like a slide I would have just said. That's good for today. All right, so let's take a look at this one here. So I think where we did sort of end there was talking about relating our E of our cell voltage, to our thermodynamic value, like our Gibbs free energy. So delta G again is our Gibbs free energy, and this is a relationship equation here. The delta G, which is our free energy, is equal to minus N, which is the number of moles of electrons. Remember, I think we talked about it, but just a reminder that that is really the number of electrons that gets transferred. So it is the electrons in both half reactions not added together. So they should be the same number, right? So whatever that number of electrons that's lost on the anode side would be the same number gained on the cathode side, and that is what N would be. So again, if you had a couple of half reactions where you had 2 electrons there and 2 electrons in the other one, N in this case is 2, not 4, so don't add them together. Yeah, so that is what N would be in this case. F is Faraday's constant, which is 96,468 really, Vogo, with 96,500 coulombs per mole. And remember, a coulomb is a joule per volt, so that is a coulomb in terms of that. So we can also relate our E of our cell to the equilibrium constant, because we miss the equilibrium constant when we don't see it in an equation. So we have this equation here, which relates E of the cell to our equilibrium constant. The R here again is the gas constant that does have energy, so it's the 8.314 version of it. Temperature needs to be in Kelvin. N is again our number of moles, and 96,500 is our Faraday's constant. Natural log of K. If you happen to be at 25 degrees Celsius, all 3 of these values here become kind of constants. And sometimes people will use a reduced down version of this equation, where it's 0.0257 volts divided by N, natural log of K. Or if you're a base 10 log kind of person, 0.0592 volts over N log of K. If you don't want to worry about those two, hey, just worry about this one and put all the numbers in, and it'll work out the same. Yeah, so you don't need to worry about the bottom 2 if you don't want to. You can put the numbers in there. I will say, depending on how you round, sometimes you might get a slightly different number on some of your answers, especially if you're solving for K and do the inverse of the natural log, the E. You'll sometimes get a slightly different number if you kind of round a little bit too much along the way. That brings us to our trifecta here of chemistry, I guess, right? So if you have delta G, you can get to delta E. And obviously, if you have delta E, you can get to K, and G and K together. I will say this equation here, people oftentimes screw up by trying to put a negative there. There is no negative on this one here, so don't put a negative there. We'll actually see a little bit later on where that equation comes from. But that is the one that we need here. So when we look at this equation here, which is our delta G basically is equal to minus NFE, that's a positive number. That is a positive number. And that means that we know a reaction is spontaneous when delta G is negative. So that is why when we roll with some positive voltage here, we do get a spontaneous reaction because we will have a negative delta G in this case. If you have a negative cell voltage, you should switch your leads, but a negative cell voltage here with that negative will turn your delta G into a positive, and that would be a non-spontaneous sort of reaction. So that's why if you do have positive voltage, E of the cell, you should have a negative delta G. And by the way, that would mean that reaction is spontaneous the way it's written, which means you would expect products to be made in that case. And that probably would mean you would expect a larger value for K as well, because you should have more products than reactants. So all those things, again, should agree with each other, the K, the G, and the E. And again, if they don't agree, then you probably messed up somewhere along the way, maybe with a sign. Obviously, same idea there. If you had a negative E, that would turn your delta G into positive, which means the reaction, the way it's written, is non-spontaneous, which means it's going to hang out on the reactant side, and you should have a smaller value of K. So once again, all those things should sort of agree. All right, so why don't you give it a go here. Calculate the delta G naught for the following reaction, and is it spontaneous? There are some SRP. Okay, let's take a look here. So in this occasion here, they did give us an equation. So we can see this guy's going from +2 to 0, and this guy's going from 0 to +2. That would be my anode, that is going through oxidation. That would be my cathode, as that is going through reduction here. Again, they kind of gave us equations. Should take a peek at it, and I maybe agreed with this. We're going for delta G, so it's going to be minus NFE for cell. So our N in this case is going to be 2, as we can see there. N is equal to 2. Our F is our constant, 96.5 joules per volt per mole. And our E of our cell is going to be our cathode minus our anode. Once again, here, I'm not going to change the sign, so I'm going to subtract the values. I'm not going to change anything here. So my cathode is 0.34 volts minus my anode, which is negative 0.44 volts. And that's going to get me here minus 34 plus basically 0.44. 0.78 volts in this particular case here. I think that's everything we need. So going in, we'll go delta G is equal to minus our 2 moles, our 96,500 joules per volt per mole, our 0.78 volts. Volts cancel, moles cancel, looking like joules is the winner there on the unit. So 2 times 0.78 times 96,500 gonna yield us a negative 150,540 joules. Or since delta G is usually given in kilojoules, about minus 151 kilojoules. We do a little bit of rounding there. This reaction is going to be spontaneous, and we see that from our positive voltage, which should give us a negative delta G, which it did. And if we calculate something like equilibrium constant, it should be a bigger constant. Any questions on that one there? All right. Let's try this one here. Will 1 molar nitric acid dissolve gold metal to form 1 molar gold 3 ion? In this case, we want to figure out, will this occur? So our cathode is which one here? Cathode is, I agree, not so much. I'm going to go with this one as my cathode in this case, which would be the nitric acid. Why is that? Because the question says, will nitric acid dissolve gold metal to form AU3 plus, which means that guy needs to go there, right? So that is actually my anode in this case. So again, a reminder that if they give you information about how it's happening, Just probably go with that information. Again, only go with the more positive one if you have no information about what's going on. So in this case, we're going to do our E of our cell, perhaps. Seems like a good move. And that's an arrow. We'll just do a kind of an equal sign there. E of our cathode minus E of our anode, right? So in this case, taking our cathode, which is 0.96 volts, minus our anode, which is 1.50 volts in this particular case, gonna yield us here a negative 0.54 volts. That, by the way, should tell us this reaction is spontaneous or non-spontaneous. It is non-spontaneous because we hit a negative E, and that means when we go into our delta G formula here, that negative and that negative is going to turn my delta G into a positive, which means it will be non-spontaneous in this case. Or you could just watch one of those old like pawn shows where that's how they test your gold when you bring it in, put a little nitric acid on it, and it's still there afterwards. Congratulations, I suppose. It kind of not there afterwards or changes colors, it's not real gold and stuff like that. So again, it's really important to make sure you do follow what it's asking so you're answering the right question. Any questions all out there? All right. All right, so what is the equilibrium constant for the following reaction? There's some SRP values there. See what you come up with. Okay, so it's anymore. This is my life. So let us solve it on that there. So E of our cell is equal to RT NF natural log of K, since we are looking for the equilibrium constant there. And that means we need to find our E of our cell so we could get to our equilibrium constant. We actually have the rest of these guys here happening as R, T, and F kind of constants. R again is our 8.314 joules per Kelvin per mole. Temperature here 298 as we need to convert it to Kelvin. And in this case, N is 2, right? We've got a little iron 2. And we got a couple of silvers with the +1, so that looks like 2 electrons there as well. Now our cathode in this case is which one? Not everybody at once. Which one? It is the iron there. There we go. And it is the iron because we're looking at the equation, right? And it's going from +2 to 0. So it is becoming more negative and being reduced, while the silver here is going from 0 to +1, becoming more positive and being oxidized. So this is our anode here, and that is our cathode. Again, I'm going to use the subtraction one, so I'm not going to change the sign, which is what we have here. So minus 0.44 volts minus 0.80 volts here. That feels very negative. 0.44 plus 0.8. A negative 1.24 volts. We know basically based off of that, this reaction is non-spontaneous, which means when we do solve for K, our K should be large or small. Should be small, right? So these are things we want to think about. So let us solve for K. Why not? I will go with negative 1.24 volts equals 8.314 joules per volt per mole, I think. And a 298 divided by 2 moles here, and 96,500 joules per Kelvin per mole. That would be good on that one. That's joules per volt per mole on that one. Natural log of K, Kelvin per mole. All right, let's clean up the right-hand side. I think we'll go 8.314 times 298 divided by 2 divided by 96,500. Going to get us a 0.012837 natural log of K equals negative 1.24 volts. Going to send that guy over to the other side. So we can go negative 1.24 divided by that answer. And that's going to get us like a negative 96 point, depending on where you want to round, I guess, 59 is equal to the natural log of K. At this point, we could E both sides, right? And that's going to get us here. And I'm taking the whole number on my calculator. So again, if you round it a little bit, you might get a slightly different front number, but the back number there for K should be okay. And that is 1.1 times 10 to the minus 42, which is again a small value K, which we would expect with our negative cell voltage and probably our positive G as well to go with that, right? Any questions on that one there? All right. So we've talked about obviously E of the cell and G, but let's talk about what happens when we are under non-standard conditions. So remember that standard conditions basically means, as we've been talking about, sort of 1 molar for concentrations, 1 atmosphere for pressures. And again, if something is not at 1 molar or not at 1 atmosphere, then sort of non-standard conditions. So similar to our non-standard G sort of equation we do have sort of a non-standard E equation as well. And that is what's known as the Nernst equation, which is this guy right there. And that is E under sort of non-standard conditions. That is E, which is our cathode minus our anode, like normal under standard conditions. RTNF, everybody normal guys. Our gas constant, our temperature, our moles of electrons, and our Faraday's constant. And Q is our reaction quotient, or again, our products divided by our reactants, again, calculated the exact same way, obviously, as you do K as well. So obviously, just like the previous formula, if you wanted to at 25 degrees, you could reduce these guys down. But again, if you just want to hang out with that equation there, just pop all the numbers in there, everything is good. By the way, that is how we get to the other equation. So if you just want to remember the Nernst equation and know how to get to the other one, you could do this, because much like this equation, at equilibrium, E is equal to 0 and Q is equal to K, which turns that guy into 0 is equal to E naught minus RT NF natural log of K. Taking this entire thing and adding it to the other side gives you that other equation we just used, and why there is no negative in this one. Yeah, so again, that's why there's no negative in that one. And it is derived from like the Nernst equation. So again, you could get to there by kind of substituting those in. Really the same way we get to delta G naught is equal to minus RT natural log of K. So kind of the same deal as how we got up there to that one in that previous chapter. So obviously you should use the Nernst equation whenever, in most cases, it's going to be probably concentrations are, maybe pressures are not obviously the 1 molar or 1 atmosphere. Any questions on that one there? All right, well, give it a go here. Will the following reaction occur spontaneously with those concentrations of iron at 0.6 and cadmium at 0.01 molar? And again, there's some SRP values to see what you come up with here. So this is definitely non-standard conditions, as those are not 1 molar. So again, to politely scream at you, Nernst equation maybe. Minus a little RTNF natural log of Q. Here our cathode is which one? Yes, I think I heard somebody whisper iron. So yes, it is iron. Once again, we're looking at the equation here. So iron again is going from +2 to 0. Again, being reduced. Cadmium going from 0 to +2, becoming more positive, being oxidized, which is our anode. So that's going to be our E of our cell there. So our E of our cell going to be my cathode minus my anode. Once again, I'm subtracting, so I'm not changing any signs here. So I'm going to go negative 0.44 volts minus a minus 0.4 volts. Too many fours. Let's get a 4 for the answer just to make sure. Negative 0.04 volts in this case. So under standard conditions, is this reaction spontaneous? It is not. So what we're going to see now is maybe by playing with concentrations, maybe we can make it spontaneous. We would also need perhaps Q. Q is our products over our reactants. So in this case, a little cadmium. And in this case, some iron 2. Other ones are solid, which again, don't get included like normal. Hence why you only have 2 numbers there given to you, 0.01, 0.6 there. Got 0.01 divided by 0.6. 0.01667. We'll do around there. All right. So everybody else should be good. Once again here, this is +2 and the cadmium is +2. So that would imply that probably 2 is our electrons in each of these cases. And I think that's everybody we need. So putting this in, we got an E is equal to negative 0.04 volts minus 8.314 joules per Kelvin per mole. Our 298 Kelvin divided by our 2 moles and our 96,500 joules per volt per mole. And I'll go down this way. Natural log of our Q, 0.01667. All right, I'm going to clean up the right-hand side of the minus. So I'm going to natural log my whole answer there on Q. And then times it by 8.314, times it by 298, hit me in equals, divided by 2 equals, divided by 96,500 and an equals. And that's going to give us an E is equal to minus 0.04 volts minus a minus 0.0525597. I don't feel like stopping this time. Why not? Just to be safe, I suppose. Keeping a lot of guard digits there. And we're going to now finish that up there. Minus 0.04 minus my answer. Going to give me a whopping voltage of 0.013 volts. Is this reaction spontaneous? Barely, but yes, it is enough to do it there. That is a positive voltage. So here, by playing with our concentrations, we're able to turn this into a spontaneous reaction with those conditions. Any questions on how to do that there? All right, let's see here. One more, maybe. There it is. For the following, don't worry about balancing. What is E of the cell and the equal? Okay, so let's take a look. So obviously we need the formula here with the equilibrium constant would be good. Once again, if you can't remember it, but you do remember the Nernst equation, as we just saw a second ago, you could get yourself there. Again, E is going to be equal 0. Q will equal K. Gets us 0 is equal to E naught minus RT and F natural log of K. This entire thing just gets added to the other side. And now we have our equation that we need for our equilibrium constant. So what do we need here? We need E of the cell would be good. So in this case, we're going to go again, our cathode minus our anode. And in this particular case, our cathode is which one? It is this one is our cathode, and this one is our anode. Again, we can see that in the equation here. The chromium is going +3. No, that's a 2. Let's try that again. Going from +2 to +3. That is becoming more positive, which means it's going through oxidation, and that would be our anode. By default, that there would be our cathode, which is going through reduction. And you are correct. That is a -2. That's a -12. That's a -2. There's 4 of them. That's like a +2.5 happening there from the sulfur on the left. Over here, that is a -2, -6, -2, and 2. That is a +2 happening there for the sulfur on the right. Not much action, but enough. It's starting at 2.5 and going this way to 2. Again, becoming more negative. Not by much, but it is in this particular case. Any questions on that there? To answer your question, yeah, you could do a decimal there on oxidation state in case you're remembering. So remember, you can have decimal or like a fraction is another way of looking at it. So let's do that then. So our E of our cell here is going to be our cathode 0.17 volts minus a minus 0.5 volts. Too many minuses. Minus and a minus. I feel like that makes a plus. I hope. Yeah, so 0.5. That's a 0.67 volts here for our cell voltage. We would then expect probably our K value to be large as this is spontaneous and it should lead us to a negative delta G if we were interested in delta G. Now we can put our guy in there. The balancing here, perhaps a 2 there, a 2 there, and a 2 there to give us the right number of electrons in each. And N would then equal 2 in this case. And that is probably about it. There is no temperature, but we'll go with 298. That's what was assumed, maybe. All right, so we'll go with our 8.314. Our 298 are 2 moles, and our 96,500 joules per volt per mole, and natural log of K, and that obviously equals our 0.67 volts. So cleaning up the right-hand side there, 8.314 times 298 divided by 2 divided by 96,500. Gonna get us, I'll go this way, I think. 0.67 volts equals 0.012837 natural log of K, bringing this that way. 0.67 divided by that, getting us a natural log of K is equal to 52.19, I believe, in this case. And perhaps E in both sides. That is not the right button. Try that again, maybe. All right, try that button, maybe. There you go. It's not similar. So we're going to obviously E both sides there. And that's going to give us a 4.6 times 10 to the 22 in this case. Once again, if you did a little bit different rounding, the front number may be a little bit different depending on where you rounded. But the back number there, I should probably be okay, I hope. And that sort of makes sense. We've got a large value of K, goes with our spontaneous reaction, which means we should be making some products here. Any questions on any of that there? All right, then let's continue, I think. So next thing we're going to talk about are batteries and how batteries are kind of similar and maybe a little bit different than galvanic cells traditionally made in the laboratory. You just need to know kind of general idea of this. You don't have to know any specific reactions for batteries or anything like that. So I'm not going to ask you like the Duracell battery reaction or anything like that. So battery is a bunch of galvanic cells or a series of galvanic cells put together that could be used as a direct electrical current. It is self-contained, which obviously makes it different than a galvanic cell you can build in laboratory with everything sloshing around in the beakers, right? Probably wouldn't want to put that into your device. And they also have slightly different things they kind of use that sort of function as a salt bridge. And they don't have a sort of a traditional salt bridge as well. So sort of a self-contained galvanic cell. So a dry cell here, I'm going with Duracell on this one as well. The anode here is a zinc can that's in contact with MnO2 and an electrolyte, right? We have our positive side to our battery and our negative side to our battery, much like a galvanic cell, right? We got our anode side and our cathode side, which is positive. I'm assuming electrons kind of go that way, yes. And as they're going out around the wire there, they're turning on your device. Unless your battery's dead, then they're not turning on much at that point. The cathode is the carbon rod immersed in an electrolyte solution. So here, that's sort of electrolyte solution, aka battery acid. It leaks all over the place. You just leave it around for too long, right? Is sort of acting as a salt bridge type of deal to keep everything sort of flowing. The voltage in this type of battery, regardless really of the size, it's AAA, AA, C battery, D battery, whatever it may be. They all have basically the same voltage, 1.5 volts. Just larger batteries have ability to keep going for a little bit longer. Here we see on our anode side here, our zinc going from 0 to +2, again, being oxidized in this particular case. And over here, it's our sort of Mn going like a +4 there, and a 6 to a +3 here being reduced in this case, going through this process. Another type of battery is a mercury battery. It's a little bit more expensive than a traditional battery, and it's used a lot of times in medicine. This also has a zinc anode, and it is in contact with mercury as well. It has a really strong alkaline electrolyte solution. Alkaline means basic, right? So, like potassium hydroxide, right? That's pretty basic. And again, that's sort of acting as your sort of salt bridge, kind of keep everything flowing in the right direction. There is no change in the electrolyte composition during operation, and that's really important for kind of longevity of batteries, is you don't have a lot of change in the components there. Also, if you end up with a lot of solids there, that's actually pretty good to keep batteries going and rechargeable and those type of situations. We do get a little less voltage out of this one, 1.35 volts, but it will last a little bit longer. Everybody's favorite battery, the car battery, unless you're late somewhere and it just doesn't work. But commonly used, obviously, in automobiles. Each cell has a lead anode and a cathode, and we basically have a series of those cells. So each one gives you about 2 volts for 12 volts, and that's enough to turn your car on. Unless, of course, you're late, then it doesn't want to turn on, I'm pretty sure. And then that's to get all the electrical systems going. Then you go, gosh, I hope it's not the alternator, right? And so it's just the battery, hopefully. By the way, we do have alternators, right? So we don't drain out our batteries as we're driving and stuff like that. It's rechargeable, right? Which, if you've been jumped before, right? They're like, let it run for 20 minutes before you shut it off, so don't call me back. You could check for good battery health there by checking its density of the electrolyte solution inside. Most of them are sealed these days. You can't pop them open usually. In cold weather, the electrolyte does get a little bit more viscous, and it results in a little bit lower power. So there's kind of a cross section there of a car battery. And the classic question of, if you're trying to jump it, which one do you put it on, right? Does red go there? Does the black lead go there? Which one goes to which? But nowadays, batteries sometimes are not even in the engine compartment anymore. Sometimes they're like in the back seat, trunk, wherever they find room to put the battery that balances it out. But usually you can still find the jumper part of it in the engine compartment. There's our cathode, our anode, and I don't know if they have so much removable caps these days. But again, here what we're seeing is our lead going from 0 to +2 in this case, again, getting oxidized in this reaction. And on the back end here, we do see our lead going from +4 to +2 in this case, and getting reduced here. As you can see, there's a lot of solid here and the overall reaction. And as I mentioned, that's really good to kind of be able to be rechargeable. Having those solid guys just provides something there for to do the reverse reaction when you apply some external current. A solid lithium battery is also another type of battery. The anode is a conducting carbon type material like graphite. It has holes in it, which will allow the lithium, as it gets oxidized, basically to travel to the other side. The cathode is a transition metal. It can be recharged hundreds of times without deterioration. And it's also a really light metal, which is why lithium, right? Power tools and stuff like that used to be a lot of lithium batteries and stuff like that used in those things. Now, a fuel cell, on the other hand, is not necessarily a traditional battery, but it can sort of function as a battery. And this is a hydrogen fuel cell, which years ago they want to kind of make cars into hydrogen fuel cells. And that's because the overall reaction here makes water, which is pretty nice. In this case, you need a constant supply there of hydrogen and oxygen sort of coming in there. And here we do see our 0 to +1 here for our hydrogen happening, and our 0 to -2 there for our oxygen getting reduced in this particular case. And again, a continuous sort of flow of this. Obviously, now we've gone more pure electric and hybrid sort of route than hydrogen sort of cars. All right, so that's again, this is a little bit about batteries, just some comparison of, how is similar and different to a traditional galvanic cell. Let's also talk a little bit about corrosion. And corrosion is returning their metals to their natural states. It's really a fancy way of saying metals that get oxidized is pretty much what's happening with those things. About 1/5 of the steel production is used to rust metals. All metals that has an SRP value less positive than oxygen is susceptible to corrosion. And that is because if you have a metal and you have oxygen, and the SRP value for oxygen is more positive than our metal, that means when it makes its own little galvanic cell with each other, this metal is now going to be your anode, right? And the oxygen is going to be your cathode, and off goes the electrons, and corrosion starts to begin, right? So any metal that has a less positive SRP value than oxygen is susceptible to corrosion. Most things, though, our corrosion in general is not always necessarily a bad thing. Sometimes corrosion can actually create a layer of protection on the surface to the metal that's underneath it. So, for example, aluminum here can form a thin oxide that kind of protects the rest of the metal from further corrosion as it does go through corrosion or oxidation. Iron does the same thing, except the problem with iron is it kind of falls off. So that then exposes fresh metal to go through corrosion. And before you know it, you've rusted through your piece of metal, right? You just crack it. Although you could pay a lot of money for patina, and that was copper, right? Making that kind of greenish sort of color as it goes through corrosion. Silver that tarnishes is silver sulfide. And gold, which has an SRP value of 1.5 volts, which is much larger than oxygen, doesn't go through oxidation and doesn't go through corrosion. And again, in this situation where we have gold and we have oxygen, the oxygen here is actually more positive in terms of its SRP than the gold is more positive than the oxygen here in terms of the SRP. And that means when these two hook up, it's actually the gold that's the cathode. And all the oxidation is actually occurring over here on the oxygen. So gold does not go through really too much corrosion. Steel, though, on the other hand, as I mentioned, is not a great thing. It has very ununiform sort of surfaces, and those are great places for like moisture to sit, and then pretty much just the trifecta of what you need: a little bit of iron, a little bit of oxygen, a little bit of moisture, and you're good to go for rust, right? So it's a nice little breathing ground for rust to occur. Actually occurs in a couple of steps. Actually, the iron first gets oxidized to iron 2, and then it further gets oxidized to iron 3 to form rust. And again, as you can see, it kind of sits here, forms this rust, it falls off, more of it gets rusted and rusted away. So you got this little sliver of the metal hanging on for dear life. Then you got to pay some money to get it fixed. It's a whole situation that occurs in that case. There are some ways, though, that you can prevent corrosion, and we'll talk about a few different ways that you can kind of prevent corrosion. Painting or metal plating is one. They sell paint called Rust-Oleum paint. That's probably why the name's called Rust-Oleum paint. So kind of protects your metal there from rusting. You could chromium and tin used to plate steel. And that again forms this sort of durable layer that protects the metal that's underneath it. Also galvanizing with zinc, kind of doing the same deal. What happens in this case is between the iron and the zinc, the one that's actually more positive is the iron, which means when we pop the zinc on there, our zinc, which is the coating up on top, is now where all the oxidation occurs. Again, protecting the iron that's underneath it from corrosion. Again, it's acting, as it says up there, as sort of a sacrificial sort of anode, again, preventing that further corrosion from occurring. Stainless steel contains some chromium and nickel that form some oxide coatings and basically gives it kind of a noble sort of potential or noble metal potential. And that's like a noble gas or noble metals, which makes it pretty much unreactive, right? And chemically inert. Cathodic protection is another way that sometimes we can kind of protect things. So for example, if you take magnesium that's connected to a tank or something like that that's buried under the ground. Obviously, if it's buried underground, there's a lot of moisture, right? So that's a good breeding ground for it to start to go through corrosion. Magnesium is a better reducing agent than iron, and things that are reducing agents are things that get oxidized. So if magnesium is a better reducing agent, when magnesium and iron get together, oxidation is going to occur again here at that magnesium and not the iron tank that you just buried under the ground. Titanium is used in ships. Obviously, there's a lot of moisture in ships and salts and all that kind of stuff. So this is the idea here. All the oxidation sort of occurring over here, destruction occurring over there, leaving whatever you buried in that tank undisturbed, hopefully. Just so many years, you gotta go dig it up and fix it, perhaps. All right. Any questions on corrosion? So again, the battery corrosion question is describe how a battery is similar and different to a traditional galvanic cell built in the lab. What is corrosion and name a couple of ways to prevent it? It's probably going to be like question 7, I feel. Do you like it as question 7? We can make a 6 if you like. I'll do 6 this time. All right, well, that may be question 6. All right, hypothetically speaking. This seems like a good place to stop because this is the last topic. I know, it's hard to believe. I can't believe it myself either. Good talk. All right, we're going to lay it up there.